I acquired this Conar signal generator for $5 about a week ago. It's a model 280, and it will go from, looks like 170 kilohertz up to 61 megahertz, which is a good range, and it's got a section, it's got a setting where you can put in a straight RF carrier or modulation, which I think is a 400 hertz tone. It's got a well-marked scale, which allows you to adjust it quite precisely. And you got an attenuator and a high and low switch. The unit didn't work when I plugged it in. I didn't get out any signal. Here's the schematic, which uses two tubes, a 6BE6 and a 12AU7. These two tubes are used as 4 separate tubes. The 12AU7 has 2 triodes in it, and the 6BE6 is used as 2 separate tubes too, which makes it a little more complicated than it looks on first glance. The circuit has a pretty conventional looking rectifier with a selenium stack, the silver or the gray thing that you can see there, and it seems to work okay. I'm going to leave that for the time being and just concentrate on why there's no output signal. As I said, there is no output signal, but I was fiddling around just trying different things, and before I had the schematic, I noticed that this was way down like that, and I moved it, and then I started getting a signal, and I noticed that there's part of this capacitor missing. It's got a chunk out of it, which I think didn't happen. I think it was actually just a manufacturing defect. It looks like wasn't completely molded. While I've checked this capacitor on a capacitance meter, and it seems to read close to what it's supposed to be. So, but as soon as I moved it out of the way, I guess it was touching against something and shorting, I was able to get a signal coming out of it. Now I get the right frequency of signal, but it's a terrible looking sine wave. And modulation, instead of 400 hertz, is more like a click, 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 click. So I'm going to have to go through this, and I suspect that this was a kit, and it was not put together properly. I almost immediately noticed a mistake in this. The person who had assembled it originally had not put this 47 ohm resistor and attached it to the high-low switch. I soldered that in. So basically what happened here was this is not connected. So the signal was going through here. So by putting in the switch in, you can switch in 47 ohms, and it'll give you a 50 ohm output. So you can take measurements with a 50 ohm output. So now it's okay in that area, but the sine wave is very dirty, even though it's giving out the right frequency, and it does give you a modulated signal up to a point, but it's not the way it was meant to be. So I'm going to go through this whole circuit and I'll find out what's wrong with it. Oh, by the way, incidentally, the two tubes, which I never suspected to causing any problem, are in excellent condition. I think this unit was never really used. So the tubes are very strong. I'll say something about Conar Instruments. As it says here, it's a division of the National Radio Institute. The National Radio Institute is well known to anyone who has been in electronics for a long time in North America. They used to advertise in the back of trade magazines and hobby magazines, electronics correspondence courses, and they had been around since about 1914, and I think they were wound up as a company by the early 2010s or so. But in 1962, they decided they wanted to come out with their own test equipment division, and they came out with Conar. This unit here, I think, is one of the first. That date code on that capacitor, 6148, might be the 48th week or 48th week of 61. So this might be one of the first signal generators they came out with. Another telltale sign that at least tells me it's from the early 60s is the selenium rectifier, which is weren't used much after the mid-60s when silicon diodes came out. So this unit is probably 62, maybe to 64. But the interesting thing is someone started making it and then just put it aside for some reason. Maybe it didn't work and they just gave up. So anyway, it's an interesting challenge to see what mistakes were made, and I'll correct them and I'll get this thing working, because everything is very clean in here. Everything just looks new. It's been obviously kept in a warm place for all these years, and there's no signs of rusting or corrosion of any kind. I don't see any leaky electrolytics or anything, except for that one capacitor. Everything looks excellent. As I go through the signal generator, I'll check it against the schematic, and when something is right, I will mark it off. I'll cross it out. So I'll start with the 47 ohm resistor on the output. I'm going to use this old vacuum tube voltmeter, which I've restored, and it's about a 1957 Heathkit V7A, and I'll use that to check out this signal generator. The top wiper of the potentiometer, the output potentiometer, has a wire that goes down to here and goes to a post there. And then that goes through a 470 ohm resistor to pin 3 of the 12AU7 tube, as we can see right here. So that measures good. So I'll mark that off now. A lot of people might not be familiar with how to read an analog meter. And so that's in ohms, and that's the multiplier scale, R times 100. And I'm reading the top scale. It's measuring, let's say, 4.2. So 4.2 times 100 is 420, so it's a little low. Although these meters are usually 10% off. But that's how you read it. The multiplier by whatever it says on the top scale. So that is close enough within specs. I'm going to leave it like that. Here we can see pin 2 is 100,000, 100K to ground. So we'll check it out. Here we are, pin 2. And I'm measuring it to ground, which is the chassis of the instrument, and I set it to a higher scale, namely 10,000, and I'm measuring approximately 10, so 10 times 10,000 is 100,000. Pin 8 says it's 1.2 K, or 1200 ohms to ground, so let's go and check it. I've connected the meter on the alligator clips to pin 8, and I've changed the multiplier again to 100, and on the top scale it says 1.275, which is close enough. Pin 7 has 100,000 ohm resistor going to ground and a 0.03 microfarad capacitor going out of that. So to measure with an ohm meter, it should be 100,000 ohms. And I've got the alligator clip connected to it, and I've got the other one connected to the chassis. I've readjusted. I've changed the scale again to 10K, and it says 10. 10,000 times 10 is 100,000. Incidentally, the way you count pin sockets is counterclockwise underneath the chassis. So you go 1, 2, 3, and etc. And you usually have a gap, and it's from the first one on the counterclockwise, and it goes around like that. So that's normally how you would count the pins in a vacuum tube socket. Between 1 and 6, we have a 47,000 ohm resistor right at the top there. And let's see what we're measuring between those pins, 4 and 6. I've moved it to the 10,000 scale, and we have approximately 4.5. So 4.5 times 10 is 45,000. Now we're going to check the other two, the 6BE6. We've got 22,000 from pin 1 to ground, and now I've hooked that up to pin 1 and our chassis, and I've got it still set on the 10,000 10K scale, and what do we read? Approximately 2.2 times 10,000, which is 22,000. On the 6BE6 tube, pin 7 should be 100,000 ohms to ground, and that's what I've got there. I've got the one on pin 7, and we've still got the meter on the 10K scale, and I'm reading about 110, no, it's about 111,000 ohms. Close enough. Now between pins 5 and 6 on the 12BE6 tube, I should measure 4.7K plus 22K, which is 26.7K. It's really tight in there to put the alligator clips. And let's see what we're measuring. We put it on 1,000 ohms range, and up at the top we've got 30. So that's 30,000. So it should be 27.28. Anyway, we're within specs. That's close enough. So we'll leave that one as it is. I was checking the power supply capacitor, the electrolytics. There's two of them in there, as you can see in the schematic. One's 30 microfarad, and one's 50. It turns out that neither of them are good. I'll show how you check an electrolytic on one of these meters. Here, I'll show what happens. Okay, there we are. It's on R times 1000 scale. Now watch what happens. This is a good capacitor. It discharges and then builds gradually up to infinity resistance. Now this is the old capacitor. You barely even have, it hardly even moves. And that goes to show that the capacitance in the old one has completely gone down to almost nothing. So I'm going to replace these two capacitors with larger values, with about 120 microfarads is what I have on hand at 450 volts. And that should work quite well. I'll see how it works, and I might change the selenium rectifier, might not. But the thing that caused these capacitors to go bad is just time. They dry out. And you can't rely on any old equipment to have good capacitors. It's just best to replace them anyway. I've taken out the old capacitors, and I'm putting in two 120 microfarad 450 volt capacitors, and I just added a little bit of glue there, and I'm going to stand them up on end and glue them in. Now I've soldered in the two filter capacitors with new wire, and I'm going to start checking the capacitors with a capacitance meter. Next, I'm going to check out this resistor, this capacitor, and this capacitor here, this 0.03 capacitor, which goes from pin 7. I'll check it out and see what the true value is. The resistor measures, it's at R times 10K, and we've got approximately 47,000. So this one end of this resistor over here goes down around up here, right up here, and connects to this switch here. So that seems to be okay, and it's connected to that 0.01 capacitor, and I'll measure that. I'm now going to measure this capacitor here, 0.01. Since it's in with other components, we'll probably measure a bit high, and then I'll measure this one here. Now, what I'm using is this ancient Weston capacity meter, model 664. This one came out in 1933, and I don't know how old this particular unit is, but it's probably from at least the 1930s, after 1933 anyway. And an interesting feature about it is it's line operated. So you have to be very careful. You have to realize that in the lower capacity ranges, so peak microfarad divided by 1,000, which would be 0.001, it puts out 110 volts. So, and then the volts go down until the highest is quite a low voltage. So you do not want to check out capacitors that are designed for low voltage circuits with this, but it's fairly accurate. I'm measuring across that disc capacitor. Where are we here? I'm measuring across that disc capacitor right there, and it says on it 0.01, 0.01, and here I'm measuring, it's on the microfarads divided by 100, so that's 0.01, and it's measuring 0.01517, which is a bit high, but taking into consideration there are stray, I'm not measuring it alone, so there's lots of stray capacitance around there, so it's within specs. Now I want to measure this 0.03 from pin 7 to the other side of the 0.01. So I'm going to take and measure. Now then again, it's going to be measuring a bit high, but as long as it's something reasonable, I will be happy with that. So it's measuring 0.04038, something like that, and that's pretty reasonable. Next thing I'm going to do is I'm going to check the continuity from pin 6 through the choke to the end of the capacitor. So we've got it hooked up, and we're measuring R times 100, and that's times 2.5, so that's 250 ohms. So we have continuity through that choke, and it's hooked up. Now the 0.1 capacitor there, that goes, one side goes to ground and one side goes to 6, I've separated from its pin 6, and that's the one with a bit of plastic out of the side, but it's not shorted or anything, so that should be 0.1, and I'm measuring it. I've got C divided by 10, so that's 0.1, and it says 0.1, so that's fine. I'm going to hook it up. This 0.005 capacitor from pin 1, here's a pin 1. Anyway, that capacitor to ground, I'm checking it. Oh, there we are, pin 1. And I've cut that out, and I've checked it, and it is within specs. It says 0.006, but that's not too bad. So I will put that back into the circuit, and I'll check the next one. I checked all the connections, and everything seems to be okay. I replaced the 2 electrolytic capacitors, and I'm measuring the voltage at the output of the second capacitor, and it's about 151 volts, which is a bit higher than what on there it says. On the schematic it says, it doesn't say what it should be on the other side, but the incoming voltage should be about 100, and I think it's at 145 volts. So the voltage is a bit high. I'm going to try it out with the higher voltage and see. If not, I might put a bigger resistor in there. Anyway, I'll check it out and see if it works. Here I've got the signal generator, and I've got a radio tuned to about 950 medium wave. And there's a straight carrier. You can hear it on the radio. And there is a nice 400 hertz test tone. I'm I'm cheating a little bit here, showing the signal on 3.32 megahertz. I'm showing it on a modern oscilloscope, but that's just what I have at convenient. So it's giving a nice sine wave there, and let's see, that's open. That's not terminated into 50 ohms. So there's terminated into 50 ohms, and still looks pretty good. It looks pretty symmetrical throughout the range up to there. It is cranked up to 61 megahertz. See if I can see it on the scope. Let's turn it back. Let's get it out of. Let's go run it again. There it's going into dual mode. Anyway, it is working very well, and there's some lack of symmetry in certain scales. It's not a pure sine wave, so that might be due to having a higher voltage than it was designed for. So maybe I will look at lowering that voltage. Otherwise, it's working very well. It's tracking and it's on frequency, and I'm very happy with it. I was looking up the specifications for the 6BE6 and 12AU7, and it turns out that both these tubes can be driven much higher than that. 156 volts on the plate is nothing. They can take 300 volts on the plate. So we're using it at less than half its output power. So these tubes are barely being used with 150 volts on the plate. Glad to know that. Now I don't have to make any major modifications to the power supply.